Good morning, everybody. I'm Sam Madden. I'm one of the co-organizers of this event, although I know very little about security or cryptography. It's like, the extent of it is, use a strong password and, keep your Linux installation patched. So there you go. That's my security and crypto talk for the day. Anyway, I'm very happy to be here to introduce this event. Thank you for coming. This is a thing we've been doing for the last 2 years to sort of highlight cool things happening in computer science in the College of Computing. So today is Security and Crypto Day, or Crypto and Security Day. I don't know, what is it called? Something like that. Anyway, we have a really awesome series of talks. A mix of people from MIT and from outside, and a mix of students and faculty. And we're going to kick it off with one of our esteemed faculty from MIT, Srini Devadas, who's going to talk about some of his work on secure hardware and cryptography and hardware. So thanks, Srini.
All right, thanks, Sam. So Sam's now my boss. So make sure you clap a lot after the talk. Maybe during, that's fine too. Awesome. Yeah, really excited to be here. I want to tell you about work that's been going on in my group and Daniel Sanchez's group. Daniel Sanchez is a computer architect. I pretend to be one. And the two of us, about 3 years ago, started thinking about hardware acceleration for cryptography. And there's been a few papers written. I want to mention Nicola Samardzic, who was really the prime mover of most of the work that I'm going to be talking about today. He's graduated, but Simon Langowski, who's one of my students, is sitting over there. So find him or me during the break if you're interested in learning more. Let me parse the title for you. Designing hardware for cryptography. I mean, that's kind of fairly obvious. I mentioned that we were interested in hardware acceleration. It turns out you can get lots of speed-ups if you're willing to build a chip, a custom chip. So I'll tell you about that. That's about the first half of the talk. And then the second part, which is a little bit more vague, but vague and exciting are kind of synonyms. Cryptography for hardware. So as we went through this process, we started looking a little more deeply into fully homomorphic encryption schemes, the specifics of those schemes, ZKPs, which I'll get to also in the talk, and started thinking about how we could kind of massage, if you will, initially these algorithms to better fit a hardware implementation. And then we started thinking about co-design. And so that's really why I wanted to give this talk here to cryptographers, the second part of this, to get a sense of whether there was kind of a cooperation and a synergy that could be created between the design of hardware that that's tailored to cryptography and the cryptographic algorithms themselves. I want to briefly tell you about a success story that is a hardware for crypto for hardware a success story, and then tell you about some work we did. It started a couple of years ago on accelerating fully homomorphic encryption and designing custom hardware for that, and then move on to the second part of the talk, which it turned out is more closely related to zero-knowledge proofs, ZKPs, and accelerating those, and then talk about what's next, and hopefully we can have a robust discussion over the break. I'm happy to answer questions. If you raise your hand, I'll stop in the middle, especially clarification questions. But like deep questions about the specific of algorithms, well, I don't know the answers to that, so ask Simon when we're done. So what is the success story? What motivated us, right? And very simple, AES, right? So what happened was AES was invented, Rindell, decades ago, and it stood the test of time. And then Intel and other hardware manufacturers decided that encryption was a good idea. People wanted fast encryption of memory, of disk, and so on and so forth. And so AES got into the hardware. And there were obviously specialized implementations, circuit implementations, and smart cards, and microcontrollers, and a whole lot of different pieces of hardware. But I think the big advance was getting into x86 processors. AES-NI was put into x86 processors. And suddenly, AES encryption and decryption was blazingly fast. It was initially put in there because AES was used in TLS, for example. Then what happened was the cryptographers discovered that when they were writing software in x86 to run on x86 machines, and generally writing software, that AES was actually faster than specialized and arguably simpler algorithms like pseudorandom number generators, PRFs, and more advanced things like verifiable secret sharing, and so on and so forth. So I'm teaching this class with the Al-Khalid this past semester, and we split the lectures since she's doing the crypto. I was doing the security lectures, but during the crypto lectures, she'd constantly say, PRF, oh, think of it as AES, right? Or PRG, think of it as AES. So it really was something where the cryptographers, it was crypto, hardware for crypto, right? As opposed to just accelerating crypto. It made a difference into the way, in the way cryptographers thought about implementing cryptographic primitives. And the reason for this, which I'll repeat, which I think you've guessed at this point, is that while the PRG algorithm, perhaps in a simple processor, would be faster than AES, written in software, the AES hardware just beats it. And so it's much better to use AES from a performance standpoint. And if the proofs go through, or based on your assumptions, sure, go for it. So the question is, now that we have all this highfalutin cryptography that's really out there, and it's been amazing over the past decade, all of these things have kind of made it into the real world, well, partly because of blockchain and cryptocurrencies, but because of other things as well, just cloud computing. The question is, can we do something like AES for more advanced primitives, which is actually intellectually, I'd say, more exciting, because these algorithms are so sophisticated and they have so many parts, moving parts to them. But then it's also more challenging because we got to pull out a primitive and then convince the hardware people to go build it, right? Because if you want to get the speed ups that I'm going to talk about, you got to put it into silicon, right? Kind of directly into silicon. So I want to tell you about accelerating fully homomorphic encryption, work that we did, which we don't quite work on anymore, but that's because we're doing better things, right? FHE, I don't know how much you know about FHE. I'll tell you what you need to know to understand the rest of the material I'm going to cover. But fully homomorphic encryption is crypto magic, right? It essentially says you don't need to know what you're computing on as an untrusted device, and you can still do the work, and you produce an encrypted result that's basically gobbledygook, and you end up sending it back, and the person who sent you this encrypted data now decodes the result, deciphers the result, decrypts it, and they get what they wanted. They figure out how much money they owe the IRS, or they figure out, hopefully they don't have this horrible disease, or what have you. You take X, you encrypt it, you send it over to the server. Server runs for a while, actually a long time, and then you get back encrypted FFX, and then when you decrypt it, you're off and running, right? And so this is the holy grail of secure computing, because the trusted computing base, at least from a privacy standpoint, is zero. There's no trust. There's an integrity issue here, which we probably won't get to in this talk, but that's something that potentially could be fixed with ZKPs. So that's perfect security. So I want to tell you a little bit about FHE, because we're going to try to accelerate it. And current FHE schemes are based on the assumption of learning with errors and LWE and ring LWE. And essentially what happens is you have a bunch of plain text, so those are the M's. And in order to get efficiency, you pack these plain texts, and these are usually 8-bit values. So you have something large, and you break it up, and then you pack it up again. And so n could be 16,000. Okay, so that's a good number to think about. So you have essentially vectors of plain text values. You add a little bit of noise to them, and then you encrypt it using your secret key. And this part we're not actually going to talk about because this is on the client side, and we're concerned with accelerating the encrypted computation, right? So you end up getting this ciphertext polynomial, which now is because of the encryption, is the giant polynomial where n is 16,000, and then the coefficients are 1,000 bits, right? So now you're multiplying these numbers, and you're going, oh my God, I mean, this, a bit turned into a million bits, and that's kind of the downside of it. I mean, it's slow as a snail, right? It's crypto magic, but it's super slow. The operations that you perform are essentially things that would obviously mimic and follow the plain text world. And when you think about vector addition and vector scalar multiplication, they're pretty straightforward, right? So they kind of mimic the plain text world. But when you actually want to multiply two plain texts, it's a much more complicated algorithm, and it's fairly complex in terms of the ciphertext world. So you end up doing things with pairs of ciphertext polynomials. And so you have the ciphertext polynomial, which is a pair for x, and you have y. And now, let's say in the plain text world, you want to multiply x and y, right? And so you end up having to do polynomial multiplications, many of them, and additions to get xy here. And this is now in the encrypted world. And then on top of that, you have these key switch hints that are many megabytes that give you efficiency. So these things, were not what Gentry put up in 2009 when he invented the first FHE algorithm. Over the years, these algorithms, because of efficiency, they do the packing, they do the ciphertext, polynomials. The numbers are security parameters. N has to be large. There's all these other parameters that need to fit exactly right. And so we haven't really done anything with that. We just take what cryptographers tell us is secure, at this point at least in this talk, and we try to go and build hardware for it. The point is, there's a lot of data here. Ciphertexts are kind of 1 million times larger than plain text, and you are messing around with these ciphertext, not in sort of a linear streaming fashion, but you're doing convolutions on them. You're doing effectively the equivalent of FFTs on them, NTTs, number theoretic transforms. And this is basically what the most painful operation would be, this XY. Well, it's actually the second most painful operation. I'll get to the most painful one a little bit later. So you can do x plus y and you can do xy. Therefore, you can do encrypted computation. You can do additions fairly easily. XY is much harder. And then the other bad thing about multiplication is this noise thing that I talked about is going to explode with multiplication. And so is another problem, right? So we'll get to that. So as you saw, we often need to multiply polynomials. And this is kind of literally grade school stuff, which is Fourier transforms. Number theory has the NTTs, number theoretic transforms, similar to an FFT. And you can do it in n log n versus n square, right? So, I mean, there's no way you can handle n square. Huge difference to n log n, so everyone uses NTTs. So the other thing that we have to exploit here is residue number systems and residue arithmetic. And that really comes down to, you have these coefficients that are 1,000 bits, right? No one builds 1,000-bit multipliers, right? It's just not tenable. This hasn't been a 1,000-bit parallel multiplier built ever. So RNS is absolutely critical in being able to do this arithmetic. And so essentially what happens is you have a bunch of little 32-bit primes, let's say, and there's L of these. And then you take these 1,000 bits and you break them up into, let's say, 32-bit numbers. And then you're running all of these things in parallel, right? So you got yet another dimension here. And so that's our primitive data type. And so you think about this 1,000-bit number, and from a cryptographic standpoint or from an algorithmic standpoint, you just say, oh, there's L there's an L vector here, or a vector of length L, and all of that is happening. Of course, there's another vector associated with the polynomial, yada, yada, yada. So all of this stuff, you now have to kind of orchestrate. And the biggest issue here is data movement. You got 1,000 bits, you got 16,000 coefficients, you got a pairs of these polynomials, you got to move this stuff onto the chip. These things are megabytes. If you do it right, it'd be fast. If you do it wrong, it takes forever, right? But the nice thing is that we can get away with 32-bit multipliers, okay, which is huge. I want to give you a sense of what we can exploit and what's hard, right? And I gave you a little bit of a sense of what's hard. So I will say that what we want to build here is an FHE interpreter, right? We're not interested in doing machine learning with FHE or doing your taxes with FHE. We want to accelerate encrypted computation, in broadly speaking. So the input is a circuit, which is what you want to compute in the unencrypted world, except that, of course, now everything is encrypted. And you also have the inputs that correspond to the input to the circuit that you wanted to compute, and then you want to get the output out. So there's two things going on. So think of it as an interpreter, and we want to accelerate the interpreter, right? So most previous FHE accelerators pick something specific, like a neural network or something, and accelerated that. But now if the circuit itself is an input, it's something where you have to obviously get a programmable accelerator, right? And so I mentioned the big polynomial arithmetic. I mentioned the megabytes. So data movement is really where it's at, right? Computation, sure. I mean, CPUs have arithmetic units too. GPUs have arithmetic units too. What is that ASIC going to do for you? What is a specialized chip going to do for you? Well, basically the same thing. But the movement that goes into these arithmetic units, the multipliers and so on, that it could be orders of magnitude, multiple orders of magnitude slower on a CPU versus if you orchestrated it exactly right. And everything is static because, I mean, you don't know squat of what you're doing. It's all encrypted, so you don't know what's underneath. So therefore, you have to take the if branch, you got to take the then branch, you got to have fixed iteration loops, all of that. So you exploit that to the hilt. So the other part about FHE, which is sort of the last messy part of it, is that this noise thing, right? You're going to keep adding noise, especially after you multiply. And essentially what this means is that resolution goes down. So you have 1,000 bits, and it gets chopped down to 900 bits after a multiply, roughly speaking. And then it goes down and down, and eventually you're going to run out of bits, which means that you've lost functionality, right? And so what happens when the coefficient bit goes to 0? Well, I mean, shit happens. You better not go there. So you got to stop. One way, which is that FHE schemes sort of evolved. Initially, there were these schemes called leveled FHE schemes, right? And leveled FHE schemes essentially said, let's go ahead and when we are running out of room, when our coefficients are getting too small, let's bail. Let's essentially go, mommy, let's go back to the client and then get them to essentially decrypt and re-encrypt, right? So you go back and forth, because the only person who knows the key is the client, right? So those are these leveled FHE schemes. And this works. It's obviously many rounds of communication, and the larger the depth of your circuit, the more the rounds of communication in terms of multipliers, the more the rounds, right? So we ended up saying, let's do an acceleration of a leveled FHE scheme, back 3 years ago. And this was an architecture specialized for FHE. And as I mentioned, this was a programmable interpreted architecture that could do any computation as long as it was limited depth, right? And so, I'm not going to bore you with the details of this. Papers have been written, and you can read it. You can read them if you want. But generally, we had hardware tailored to FHE operations. And the orchestration of the data movement, which I have a compelling example of a little bit later, was really the key with respect to getting speedups. And the speedups were enormous. Now, I will say this is a design that was built as a hardware description language. And there are efforts by Intel, for example, to build silicon using roughly, and I'm not taking credit, but roughly this type of architecture. And they're startup companies. But and the reason they're actually building hardware is because you can get 3, 4 orders of magnitude, right? I joke that we've taken the snail and turned it into a tortoise, right? It's not quite, a hare yet because you still have a few more orders of magnitude to go with respect to the overhead of computation. But 3 orders of magnitude, ain't. Well, I mean, it's not bad, right? It's pretty good. So you can now do things that you couldn't do before if you had this hardware. And the big issue, really, as we got through the first part of this talk, or the first part of this research effort was, this leveled FHE is sort of not particularly satisfying. And you had this communication cost, and this large communication cost was really going to slow things down if you wanted to do interesting things, right, like deep neural nets. So people invented bootstrapping in the FHE researchers, and it's an expensive procedure to refresh ciphertext, and this is even more complicated, this procedure, than multiplication, obviously, or the key switching, and uses that. And the idea is that before you run out of room, you effectively do, you do a decryption and a re-encryption in the encrypted world. It's really magical. I don't understand it. And you go back and forth. You have the sawtooth thing where you get down to, let's say, 200 bits, and then you rise up again to 1,000 bits, and so on and so forth. And so as we have to, even in the leveled FHE, you do have to perform computation at multiple bit widths, and you want to exploit that. So the nice thing is that RNS allows you to exploit that because you can have fewer 32-bit multiplies, when you have a coefficient that's like 500 bits versus 1,000 bits, right? So you want to exploit that because there's a large factor there, and you don't want to leave any speed up on the table. So some observations. Communication is really hard to accelerate because the network cards and the hardware for switches and routers are very hard to change. They have to conform to standards, and the physical layer is very hard to accelerate. It still takes the same amount of time, to get across the internet from here to California than it did as it did, 10 years ago. Obviously, computers have gotten more parallel and faster. And the other part of it, with respect to computation, which I want to stress, is Amdahl's law. That's Gene Amdahl, who said something that's really, it's common sense. And my interpretation of it would be, let's say that you wanted to get a huge speed up of 100x. Well, what that means is you can't even ignore 1% of the computation. Because if you didn't speed up 1% of the computation, then you're limited to 100x. If you didn't speed up 2% of the computation, you're limited to a 50x speed up, right? So when you design hardware accelerators and you want a 1,000x speed up, it basically says you got to accelerate everything. You can't ignore anything, right? There's no bottlenecks. I mean, everything is a bottleneck, okay? And so if you look at bootstrapped versus leveled FHE, and I'll tell you about this second processor, at least a little bit about that we designed. You compare them, and you say, with bootstrapped FHE, it's very complicated. There's a lot of computation, but very little communication. In leveled FHE, it's the other way around. So hardware acceleration can give you this picture, right? It basically crushes the computation down through this ASIC design and doesn't touch the communication. And so if you had a deep circuit, you absolutely need to accelerate bootstrapping, right? So that was kind of obvious to us as soon as we've kind of finished the F1 project. And so then we moved to thinking about how to accelerate bootstrapping, which was, and then read it. I mean, this was design 2, so we changed our minds about a bunch of stuff. And so this is a vector processor that's a very wide vector processor. And then in order to store everything on the chip, and this is a big chip, by the way. Think of it as a multi-core processor, but these ciphertexts and these polynomials were all stored on the chip, and so the scratch pad single-level register file is 256 megabytes, new functional units, and I want to tell you about this data movement and give you an algorithmic innovation that was due to Nicolas Samarczyk associated with the pipelining of all of these operations that I've told you about, namely the polynomial multiplies and the key switching and so on and so forth, right? So you have this vector data path that's 2048. I mean, this is just 16 here, but it gives you an idea. And you can chunk these things. So if you have 16,000, remember, and you only have 2048, you do have to chunk there. And so this is just a simpler example where you have to do some chunking. And in hardware, if you have a data path that's 2048 lanes wide, vector adds and multiplies that act coefficient-wise are easy, because you can just sort of pipe them across. You can just sort of have this lane, and you're just piping it across, right? So it's easy to pipeline. But NTTs are convolutions, and automorphisms are transposes and permutations. So you're picking things from all over the place, right? This is the reason why GPUs and CPUs are really slow, right? Because they have to do this one at a time, right? So there's this sort of this order n, built in to picking things out, not because necessarily of you can break that down with parallelism, but the movement that gets the data from the output of one multiplier to another, or in these intermediate steps, is this linear computation, because you're doing this, pulling into the register file, going back, and so on and so forth. It'd be great if you could do things a little bit better. And so here's a pattern of data movement, which is a transpose. And CPUs and GPUs can do some chunking, but effectively think of it as order n. It's, maybe the constant is smaller than 1, but they're not good at this, right? And here's something that they're even worse at, right? So in FHE, you have to do something like, for the exponents, index times 3 mod n, okay? And so now you got to do that, what I have here. And this is order n on a CPU or a GPU, right? So in Cradle Lake, it turns out you can do this in constant time, right? Roughly constant time. And the reason for that is that is Nicola's ideas on you take you have a two-dimensional chip, so you took that 16 vector and thought about it as a matrix, and now you think of this as you want to transpose this, or you want to do this other automorphism on it, and think of this polynomial as spanning the whole chip, basically, there's a two-level transpose operation, which corresponds to a local transpose, and then a permutation. And both of these things are fixed permutations. And it turns out you can take NTTs or automorphisms and decompose them into these transposes. And each of these transposes is 2 levels in the chip. And you, with 1 per NTT and 2 per automorphism, you can essentially do the operations that you need for the CKKS scheme, for example, right? So suddenly now you went from order n to essentially order 1 for this part of the computation, right? And so you can imagine that, and similar things would have happened in F1 as well. You can imagine that that's where the speedups came from, right? So it's not the computation parallelism that gave you the speedups, though that's really essential because CPUs have that. But it's really the data movement that gives you the big wins. And so it's 5,000 times faster than a 32-core processor. So that goes back to saying that the parallelism wasn't where it was at with respect to the speedups, and does better than F1. But here's the bad part about it. $20 million. Anyone has $20 million handy? We'll build it for you, right? But so Intel's building one of these, and there's a startup company that probably in stealth mode in Europe that's building one of these accelerators. But this is really kind of the rub of hardware design, which is great. You motivate people by getting these large speedups. No one is going to build hardware if you tell them that it's going to be 5 times, 10 times faster than their CPU. It's just not worth it. So you motivate them by getting these types of speedups, but then you got to go build it, and it takes years, and so on and so forth, right? So, but that's life. That's the story. So, this was about a year, 2 years ago, and we don't work on this anymore. But it turns out, the people are continuing to work on it, and architects have follow-ups on F1 and Cradle Lake, and things are a little bit better now with respect to the size and the speed. But I want to move to the second part of my talk, which is really kind of looking more closely. I told you I didn't know much about FHE. We did this work anyway. We knew enough to do the work. But can we do better in terms of making this process easier, because the hardware is easier to build, by tailoring algorithms themselves, right? So verifiable computation, kind of the analog of FHE. I'm not going to say very much about the specifics of this, but the basic idea is you want integrity, untrusted device. You want to ensure that it's done the computation correctly. Now, ZKPs have this additional privacy property that says that you have a witness and you don't have to give that away as the prover can keep some secrets, from the verifier, but that's not central to anything that I'm going to talk about, right? So think of this as the integrity analog of FHE, all right? Same problem, super slow if you run it on conventional processors, and so hardware acceleration would be nice, right? So there's a whole bunch of VC schemes, right? There's a ton of them. The basic idea is that you want the evaluation of F to be something that you don't want to do for some reason, because it's going to get much slower when you ask someone else to do it. And maybe it's because of the privacy requirement. But it may be the case that if the verification time is smaller than the evaluation of F, that you'd rather someone else do it. And of course, the proving time is going to be way larger than the evaluation of F itself. And that's what we'd like to address. And I mentioned the zero knowledge. And so there's some scenarios where the client can't execute F on its own. And so you want to be in that situation because that motivates the work, right? So there's a lot of applications. I don't want to get into that. The Groth scheme is the most popular and the most used scheme from 2016. And it's got tiny proof sizes, okay? It's basically 3 words, or call it a kilobyte. It's a compute-bound algorithm, and it uses elliptic curves. And it turns out you need, and this is something that you should look at and go, whoa, this is a problem, because I told you about multipliers. It needs 381-bit multipliers. Nobody builds these, right? So there was one piece of work before the work I'm going to describe to you on accelerating ZKPs, and it was called PipeZK. It published in an architecture conference, and they got 5 to 10 times speed up. And I won't repeat what I said about minuscule speed ups, not motivating hardware people. I guess I just repeated it. But as you can imagine, this didn't go anywhere because of the small speed up. You could use parallelism and at maybe at a higher level and get this type of speed up. And so why, right? And the main reason is this multiply, and I'll tell you a little bit more. But it turns out there's a whole bunch of ZKP schemes out there, and things, Groth is not, kind of could fit into this modular ZKP paradigm, but if you kind of jam it in. But in general, if you look at the ZKP world, there's IOPs and PCSs, so interactive oracle proofs and polynomial commitment schemes, and you can kind of plug and play, right? You can pick an IOP and you can plug it into this PCS or use a PCS for it, and vice versa. And so generally, you translate IOPs, translate things into a polynomial structure, and then you commit to computation by committing to polynomials. And so that's your ZKP, right? So the PCS universe, there's curve-based things like Groth, hash-based things that have been around for 3 or 4 years, and then there's lattice-based things that are emerging. So we looked at all of these things and said, hey, okay, from a hardware standpoint, what works, right? So some of it is just choosing things right, and then there's actually massaging things, right? So you'll see a little bit of both of those. And so I want to contrast the first 2 kinds. The curve-based PCS have downsides. They have tiny proof sizes, but they have complicated curve operations, like in BLS, and you end up having these large multipliers. And it turns out there's a lot of data-dependent control flow, which kind of goes against the grain with respect to pipelining and not having pipeline bubbles and changing your mind about what you want to do sort of halfway through, and which is a problem in hardware. Hash-based PCSs take advantage of fast hardware operations. I mean, SHA-3, right? Have an array of SHA-3s and parallelize to your heart's content. And you can also play around with these moduli and do things right. You have tree and matrix structures that are easily parallelizable, but here's the downside. Proof sizes are much larger. We're talking 2-3 orders of magnitude larger, right? But the nice thing is that you go from kilobytes to megabytes, okay? Big difference from going from megabytes to gigabytes, okay? So constant factors, this talk is a lot about constant factors. It turns out where you are in terms of the kind of the range of constant factors is a big deal. So kilobytes to megabytes is okay, megabytes to gigabytes is not okay, okay? So we looked at a bunch of things, and then we zoomed in on Spartan and Orion, and decided that these map best to hardware. We've kind of changed our minds about this, but this was about a year ago, and decided to go with this, right? So now let's look at this. It's a little bit different from what I showed you before, but here we have Groth16, and it turns out Groth16 is slightly faster on a CPU than the Spartan and Orion thing, and it also has less communication, right? So you're kind of going, what? Yeah, but it turns out because of what I told you about the curves, you can absolutely crush the Spartan and Orion computation, by 1000x if you did it right. And so it turns out, even from an end-to-end standpoint, even though you're paying more, partly because of the kilobytes to megabytes and existing networks, which are megabytes per second, you can do better, right? And I'll give you some specific numbers, but this is the basic idea, right? So again, a choice that's perhaps counterintuitive because you were worse in two fronts, but when you look at it in a different substrate, it's actually the right thing to do, right? And so Spartan and Orion have a bunch of different things inside of them. Sparse matrix multiply, sum check protocols, polynomial arithmetic, Merkle trees, Reed-Solomon codes, and we got to speed up all of them, right? Because of Amdahl. And it turns out if you kind of look at a little bit, inside of it, the Spartan IOP uses essentially the sparse matrix vector, and then Orion uses the other ones, the PCS scheme. And if you look at these low-level tasks, there's basically a small number of functional units, which are listed here, that correspond to running all of these things. And they're used in many different tasks of Spartan and Orion, but that's kind of the mapping, right? And so now if you kind of look and you say, well, these things take 2%, and you go, oh, in a different world, 2%, I don't care, right? 98 or 100 looks pretty good. But if you want 1000x, well, you got to speed up to 2%, right? There's no two things about it. And so I just wanted to point that out, just more concretely than I have previously. And so this thing, NoCap, is a design of a programmable accelerator. Same thing. You have your circuit, and the circuit is an input, and you also have your inputs to your circuit. And it's a vector processor that supports vector modular multiplication and addition. One of the things that's interesting that I'll get back to is in this hash-based world, it looks a lot more like the FHE world, not exactly, than the elliptic curve world would look like the FHE world, right? So we were looking at this and going, oh, we've kind of done this before, or something similar to this before, right? Looking at our, thinking back on our work on F1 and Crater Lake. It turns out for the tasks that I mentioned, the 5 tasks, the primitives that are underneath, it turns out they have different requirements. So you end up wanting to have a very wide lane processor, 2048, which is the same as at Crater Lake. When you want to do, for example, vector multiplication and addition, but when you want to do hashing and NTTs, you want something that's slightly that's narrower. Static control is a big deal. Same thing. I mean, it's you have to do things without knowing what you're working on. I mean, it's not quite the same as in the encrypted world, but since the prover has to produce a proof, it's similar in that sense. So you can do a lot of prefetching and scheduling. Data movement is important. So these pictures are pretty, I don't think they're going to tell you anything other than the fact that you actually have 2 different modes of operation. And the way you want to think about this is that sometimes you want to use 2048 parallelism, and you think about these things as all running, all these square banks and processors running in parallel. And sometimes you're running them in series, in sort of, they go pipeline from left to right in terms of 16 steps of computation, right? So those are the kinds of things that you'd have to do in order to in order to target the 2% and the 69% or the 18%, right? So that's where it's at. So I just want to give you a sense of one optimization like I gave you for the transpose unit that was important here. Let's take a look at the sum check protocol, which is a large fraction of the time. It turns out the things that you have to do are you have an input, n is large, and it actually blows up to like something like 20n or whatever. In this example, I have 3n. And so you're streaming this input onto the chip. And this is not going to fit in these register files. And as you're doing this, you're reducing this input, and you're computing a hash for it, right? And this is kind of something that happens in the sum check, right? You produce R1. You reduce R1. Then what you do is you're going to try and this algorithm is going to fold this. So you actually have to take the 3n that you computed, and you got in the naive algorithm, you're going to stream it again. And now you're going to use R1, and you're going to fold this into something that's 3n over 2 by multiplying the first half with R1 that you computed in the first step, and then multiplying the second half by 1 minus R1, and then you get an output that's 3n over 2. You're going to reduce, as you're doing that, you're going to compute the R2 hash of the 3n over 2, and then you're going to repeat this process, right? So think of n as not fitting on the chip, but something at half of n might fit on the chip. And what you're working with initially is maybe like 20n or something. So you got many levels of this, right? So now let's say you have R2. What happens now? Well, you got to load the 3n over 2 again because that doesn't fit on the chip. And you got to do this folding again. And then you get down to 3n over 4, right? So at some point, everything is going to work out because everything fits on the chip. But I want to talk a little bit about the optimization that we made that was fairly important. Not super dramatic, that speeds up this part. So essentially, it's recomputation. It's like do the work again, because that allows you to not store more things, right? Because you can just generate on the fly. It's not obviously a paradigm that's been used many times. So assume you have R1 and R2. Then the idea is that once you've gotten R1 and R2, in order to do this previous thing, which is getting the 3n over 4, you go back to the original input, stream that in, expand it on the fly, and then do this computation, right? So essentially do pairs. So nothing profound here, but important from a data movement standpoint, right? So that's why I wanted to point this out. So there's a whole bunch of things that I won't bore you with that correspond to things like that. I just wanted to give you one evocative example. So in this simplified example, you save traffic. Maybe you get to factor 2, or recursively, maybe it's more, right? So this is super advantageous to when the sum check size is large, which is usually the case. So so we took the Orion Spartan code. Simon took this code and sped it up by about a factor of 5. So we're going to compare against the sped up version on a CPU for fairness. And you can get about 500x on the proof generation, again, if you build this hardware. But we've been fairly careful about getting a hardware description and doing all of those things which are necessary in the world of computer architecture. I wanted to mention, this is just proof generation. But going back to the trade-offs, really, it's about sending the circuit over, getting the prover to produce the proof, coming back, verifying it. Well, there's network transit here, right? And we can't ignore that, right? But if you look at the proof sizes, well, it turns out that you do pay. Sending a kilobyte over the internet is, it's not 1,000 times faster than sending a megabyte over the internet, but maybe it's 10x faster, right? And so you assume some network link and include that latency in the verification time, and you're still like 20 times faster. So provided you had this hardware, it's a good idea to go ahead and go to larger proof sizes, okay? And so that's kind of the lesson we learned from it. Still, it's a smaller chip than Cradle Lake, but hey, someone has $10 million lying around, we'll build it for you, right? Yeah, go ahead.
So the one-time cost?
No, so yes. So this is the capital cost. I'm talking about the capital cost, right? Now, if you now, depending on volume, so that's a totally different conversation. It's a great question. I'll give you a better answer, but the short answer is what I'm putting up is capital cost, and then if you were going to sell 1 billion of these, there's a lot of people who would give you that, give you more, right? In fact, if you just, that's right. If you claimed you could sell 1 billion of these, you could do that, right? So I want to finish up telling you about, I think, a level of co-design and hopefully intrigue you with thinking about these kinds of problems that we're looking at, that Simon, myself, Daniel, and Yupeng Zheng have been looking at in terms of what's next, right? I think Vinod's question may get answered here a little bit as well. So one of the things that helps with hardware is a number of users who want to buy your chip, as I just mentioned to Vinod. And one of the things that that is nice about the ZKP accelerators and the FHE accelerators is this picture, right? So which is essentially that you got a bunch of different schemes that kind of have similar primitives, right? And this is kind of the game. I mean, AES was a primitive, right? It's a very basic primitive. So can we discover primitives that would be useful? And then you get the Intels and the AMDs, you go put these primitives in there, and everyone's happy, right? So if you look at these checkboxes, they're kind of similar in the first three, and the last one, which is the elliptic curves, is quite different, right? So this sort of tells you that that maybe if you want to go build a universal cryptographic accelerator, that you should be thinking about hashes and maybe lattices, and not as much about elliptic curves. Okay. So that's one thought, right? Which is can we do something, and we have some thoughts on it. There's a distributed ZKP world where you say, well, let me build a chip to handle a circuit of size S, and that's a big chip, and therefore it's super expensive. So it's nonlinear. If a chip is twice as large, it's going to cost you, capital cost is going to cost you twice as much, right? I mean, even the volume cost would be about twice as much, but the capital cost is really super linear. Pianist is a DZKP, distributed ZKP, based on the Planck IOP, and it does chunking to go take, go run stuff on Amazon clusters and so on and so forth. So this is just purely software. It uses a curve-based PCS. So Simon's been looking at, with Yupeng, looking at replacing this distributed ZKP, curve-based PCS with hash-based PCS. And it turns out you can imagine a distributed architecture where you have smaller chips, but then you build a board or a multi-chip module of these smaller chips that may be a tenth of the size. And the big question is, when you go off-chip, it's much slower. So you don't have that much bandwidth. It also takes a little bit longer. So you have to structure your algorithm such that the communication across these things, so this is really going back and redesigning Planck a little bit with respect to the chunking, to essentially say things like, I'm only going to communicate hashes as opposed to these NTTs, okay, across these chiplets, which are much smaller. And so now, it's much cheaper because, and maybe this is an academic project where you build a little a chip that is, a tenth of the size of this bigger one, and then you build a board. You can get, 10 of these back, obviously. You need 10 of these, and you build a board, and it only works if the algorithm is structured in such a way that the communication across these chiplets is much smaller than the communication that's required inside of the chiplet, right? So that would be a co-design of the algorithm, which is kind of ongoing, and we're happy to tell you more. So that's it. My final thought is there some notion of acceleratability that can guide cryptographers? I've given you a bunch of interesting ideas, hopefully intriguing ideas, but I haven't synthesized them. And did I promise to? Well, maybe I did, but then I lied. But I haven't synthesized them into a metric that essentially takes in the fact that going off chip is painful. Data movement is where it's at. Parallelism is easy. Pipelining is easy, but certain kinds of pipelining are hard. And so, how would that change, the way if a ZKP expert, and we're kind of trying to do that with Yupeng, if a ZKP expert, went up from first principles and said, I want to build the optimal hardware and ZKP together, right? What would we come up with, right? And so, hopefully you're intrigued. Thanks. Yeah. I had no idea how long I took.
Pretty good.
Okay. Right. Awesome. Yeah, happy to take. Yeah, Vinod. Yeah. Forgive. Okay, that's a good word. Yeah. Yeah.
So now, how does the ongoing cost, compare to doing this with an FPGA, for example?
So yeah, Daniel has a board that looks like that. And each of those things are an FPGA. The little squares are FPGAs, right? He's got, I don't know what it is. So you're absolutely right. So that's so FPGAs have issues. You pay a factor of 10 in speed. You're running at 100 megahertz as opposed to a gigahertz. And that you definitely pay. The other part that you pay, which is an additional factor, is the amount of stuff that you can put on an FPGA. So in some sense, you got a factor of 10 because of the circuit size shrinking, but you blew up by a factor of 10 because an FPGA has lookup tables and can't do it. But that's okay because the FPGA has already been built, right? And so you buy that. But there are thousands of dollars, right? And so you could imagine building big FPGA, taking a big FPGA and building a board like this, a 3x3 board like this, and maybe doing this Plonk thing. And now you're in good shape. Your capital cost is in the thousands of dollars, tens of thousands of dollars, as opposed to the 20 million. There are some challenges that are associated with, permutation networks on FPGAs, unfortunately, right? So, the one downside, there are probably other downsides, but the first thing that comes to mind is you got these lookup tables, and you got to structure this stuff exactly right, and so the permutation networks and all of these things that I talked about, they're not that great on FPGAs. There's a lot of work that needs to be done in order to make them competitive, and you could imagine doing that work. But it's a perfectly reasonable path to follow, and I think from an academic standpoint, it's probably the path to follow.
Okay, cool. One more question, if I may. So, let's again assume that the 20 million is forgiven, right? What is the sort of the marginal cost of building each chip? Is it more like 10K?
Literally, what you do is you go to a TSMC and you say, I want a billion of these, or you want a million of these, and depending on the number, there's latency with respect to when you actually get a run, right? So that might take you a while to get the chips back because they have other customers and they're filling their pipe too. And the other part of it is the cost, and so if you're willing to commit, you're probably it goes down for sure. Anant Agarwal used to say, a million of anything, meaning a million of any chip is $1 each. Right, that's what he used to say that, right? But I don't believe him. But that's reasonable. Obviously I'm quoting him. But it's a pithy way of describing that. Once you get to volume, the actual chip cost it really shrinks, where you're not worried about it.
Yep. So I guess my question really was about FPGA versus ASICs.
Right. So in
the FPGA,
the FPGAs, they have it's a little bit like GPUs, Vinod, where there's a margin. So if you want to go buy FPGAs from Xilinx or GPUs, you're paying a lot. So now, if you're willing to live with that, so there, I think, there's an expansion factor. If you are the chip designer, you could get this $1, right? Because you're actually building it. Now, of course, you're selling it for 10. So there's a markup there, which but I think that's certainly not as bad as the capital cost.
Okay. All right. Thanks.
Yeah. Go ahead. Go ahead.
Amazing talk. My question is about the hardware acceleration part. So you mentioned the main problem that is arising, it is because of the data movement.
Yes.
So if we were to design some hardware accelerators for all these cryptographic algorithms, and we try to make sure that this data movement is reduced. By what I mean that is like if you're feeding a large bit stream into an accelerator, I would want that bit stream to be processed within the accelerator without sending it back and forth again and again.
Yes.
So can we think of like some methods in which, so for example, as you mentioned, like we cannot build very large multipliers, but like, can we think about like some innovative schemes in which we can do the multiplication, but without doing this back and forth again and again?
Multiply. are well researched, right? So so I can't imagine that well, certainly I can't imagine myself coming up with a new multiply algorithm. But I think that at a level higher than that is where we're working, right? Which is sequences of multiplies and feeding the output of one multiply into another, and making sure that if it was on the chip and you're right there, you grab it and go, right? But if you needed to move it, well, even to a different bank of registers or a different scratch pad, you lost a little bit. And the game is over, and you've lost if you have to move it off chip, right? So it's complicated enough that I don't have a handle on kind of this this beautiful scheduling algorithm that would do it exactly right, because it's very constrained, and the numbers are important because how much you can store. Spilling is bad, as I mentioned, but that's kind of the crux of the matter. I mean, I think that you put your finger on exactly the problem. A general purpose algorithm to solve it, I think, is probably feasible. Now that algorithm now is your cost model for this accelerability metric that I mentioned to you, because you want to say that, assuming you had this beautiful algorithm that would do the scheduling properly, and then that tells you what your cost of data movement is. And now your actual cryptographic algorithm should use that, right? As opposed to this order n square. It's like you tell it to order n square, it's going to come up with the wrong thing. You tell it that you give it a better metric, it's going to come up with the right actual overall design, right?
Right. That's a great insight. So another related question to this is...
Why don't you go to Iran, maybe, yeah. Yeah, well, yeah, sure. Vinod got 3 questions, Well, yeah, but he's Vinod, yeah, right, so, yeah, right, so.
I know some cryptographic algorithms have a problem with side channel attacks.
Yeah.
And so are there any issues with that in either the design of the hardware or its use?
Great question. So in the FHE world, we basically say, side channels be damned, because it's ciphertext and you could see the ciphertext, right? So that's fine. In the ZKP world, it's nuanced, because on the prover side, you got to be a little bit careful, because there's the ZK part of it, which is the witness, right? And so you don't necessarily want, as you're doing it, you don't necessarily want to leak the witness. So we honestly, it's a great question. We kind of ignored it. And that's why I said, don't worry about the ZK part. This is about the integrity. And so you have to kind of look at it a little bit more carefully. I think for the designs that we have, the fact that it's static control, the fact that everything happens kind of the same regardless of the bits, is a huge help, right? So that's pretty much all I have for you, right? So yeah, Iran had a question. Yeah.
Thank you. Well, first, thank you for this talk. Clearly, these are exciting times for the cryptographic techniques for protecting general computation, and I think that this kind of acceleration is essential for it to have to fulfill the practical promise. I have a question about handling faults. As we know, in VLSI design, making sure that faults have low enough probability is a traditional design criterion in ASIC design. But in some cases, you may be able to afford faults, in which case you can push your clock rate faster or have more aggressive design rules and potentially get a lot of performance. Now, we know that in some contexts, when you have specific algorithms like the ones for factoring, you can afford mistakes because you can compensate for them at a higher algorithmic level. And I wonder if we are looking at that pattern again here. For example, in the case of verifiable computation, you may be able to afford occasional faults as long as you can catch them through the very mechanism of verifiable computation. Or in the case of FHE, if the faults end up just increasing the noise that you handle anyway, they may be absorbable. Have you looked at that?
No, we haven't looked at it, but I think I want to say that Ajay Joshi has been looking at things that maybe not exactly that, but you should check in with him. And he's written some nice papers on FHE acceleration in particular. He's at BU, for those of you who don't know him. Yeah, so I don't think I have a great answer for you, Ron, but I will say that in in the context of static control, it is an exploitable mechanism to, fault tolerance is easier, right? Fault tolerance is really difficult when particular faults are much worse than others, but maybe they have a lower probability. When it's kind of heterogeneous like that, it becomes a much harder problem. In the context of the designs that we have, it's very homogeneous in the context, in the sense of faults, right? So it's going to be, well, the pipeline went through or not, there's no data-dependent control flow. But I think the other part that perhaps is the more exciting is exploiting the, well, having fault-tolerant algorithms themselves, right? Which I think is kind of a little bit orthogonal to accelerators in the sense that those would be useful in the CPU as well. And the combination of that, I'll have to think about. But it's certainly something that should be exploited, for sure. Right? Thanks.
All right, we're out of time, so let's